Okay, so to start with, I'll give you a brief introduction and overview of today's talk. I'm going to start with the basics, an introduction to ore loss and dilution, its implications, move into how to measure blast movement, then we'll talk about how to model and some of the recent developments in modeling blast movement. I'm then going to spend a fair bit of time on discussing a new stochastic model developed by myself to measure and model blast movement. And all through the talk, I will refer to case studies in each of these separate parts of the contents, and then I'll finalise with some conclusions and questions. So by way of an introduction, drilling and blasting is required in most open pit mines to fragment and loosen the rock mass. It's the very nature of blasting that causes the rock mass to move, and it's in this movement of the rock mass that can cause blast-induced ore loss and dilution if the post-blast grade boundaries are not accounted for. So by way of definition, ore loss occurs when valuable material is sent to the waste dumps and hence never recovered. And dilution occurs when waste material is mischaracterized as ore and is either sent to stockpiles or to the processing plant. So there are a lot of causes for ore loss and dilution. This talk predominantly focuses on open pit, but many of these can also be applied to underground. So causes are inaccurate definition of the ore body, improper blast design, blast-induced movement, inappropriate excavation methods, excavation equipment size, and the method and direction of digging. Today's talk is going to predominantly talk about blast-induced movement. So how does blast movement cause ore loss and dilution? This slide is going to address that in way of a demonstration. If we take a simple ore body, we have sections of high grade, low grade, and waste. Prior to blasting, these boundaries are well defined by blast hole assaying, by grade control drilling, and in many cases, if mining by flitches, they're also defined for each flitch. We then come along and we blast this material. In the process of doing this, these sections of high grade, low grade, and waste are displaced. Now, if the blast movement is not accounted for, and we use the same pre-blast boundaries from the blast hole assays to recover the valuable material during excavation, the result is sections of ore loss and sections of dilution. So what are the factors affecting blast movement? There are many factors, starting with the rock mass itself. So the strength of the rock mass, the density of the rock mass, the structure. So you can imagine a rock mass predominantly made up of clays or sand material is going to move very differently to a hard homogeneous rock mass of, say, granite or diorite. Blast confinement conditions, so whether the blast is free-faced or choked. Blast design, so factors such as the powder factor, the geometry of the blast, so how big the blast is, will affect the blast movement. The initiation sequence, so whether it's designed to along the echelon or if it's fired with a free face, with a choke blast or a V initiation, will all affect the blast movement. And the blast QA/QC, so how well the blast design is implemented in the field. So if a designed stemming height of 3.5 meters was implemented, how well is that adhered to? Charge weights, if 200 kilograms of charge was designed per hole, did we actually get 200 kilograms per hole, or some blasts or some holes with more or some holes with less? Each of these factors, there is inherent variability associated with them. So the rock mass isn't completely homogeneous. It is going to vary across the blast. Blast design factors are going to change. So a blast powder factor design of 0.5 kilograms per tonne, no matter how hard you try, you're not going to get 0.5 kilograms per tonne for every single hole. There's going to be variability in these. Okay, so a couple of case studies. So why measure blast movement? I think we addressed that in the introduction, and it's to reduce oil loss and dilution. But if we look back in history, this was made very evident by Zhang in 1994, where he conducted a survey of 27 gold mines in Nevada, all open pit. He found at the time that most mines used smaller powder factors to control blast movement. That was the mode of operation at the time. He also found that only a few operating mines actively monitored blast-induced rock movement. And of those mines that actively monitored blast movement, there was only one that he found to occasionally adjust pre-blast grade boundaries to account for the movement. So this was 26 years ago, so we'll see how far we've come. In 1995, Taylor also monitored grade control versus crusher discharge grades for the Rochester mine in Nevada. And he found that all control grades were consistently higher by an average of 7.6% and on occasion up to 25%. Taylor estimated for the Rochester mine during 1994 alone, if blast-induced movement had been accounted for, the mine could have produced an additional 4,500 ounces of gold and 200,000 ounces of silver. This would have added 2.7 million in annual revenues for the Rochester mine in 1994. And this was at a time where gold price was at $380 an ounce. So even then, significant value to be added to the operation. And to prove that it's not just gold mines that need to account for blast movement, in 2007, Belfield measured at the Tallering Peak Mount Gibson iron ore mine in Australia. So the economic impact of not accounting for blast-induced movement equated to an ore loss of about 28% and a value per blast of about $46,000 Australian. Okay, so we've demonstrated through these case studies that it's obviously important to measure blast movement. So what are the techniques? Well, how do we go about measuring blast movement? Over history, there's been a number of authors and a lot of papers documenting ways to measure blast movement. So if we start with the beginning, some of the simplest methods involve visual surface markers. These are addressed by authors such as Davis et al. 1989, Morley McBride, O'Brien and Cutts, and Zhang. So these methods include flagging tape, they include drums, stakes. These methods have been shown and are still used today. Very quick. The advantages are they're very quick, they are low in cost, and they cause minimal minimal disruption to the production process. However, they do come with a number of significant limitations, and these are often poor recovery of the markers, usually in the range of 20 to 30% recovery. And what they fail to do is they do not measure the subsurface movement. So they don't measure what's actually going on below the muck pile. In 1994, Zhang, and in 1995, Gilbride and Taylor introduced or documented the use of coloured sandbags. And this was to look at movement below the muck pile, to actually measure movement what's going on below the surface. They found that by placing bags into specially drilled holes for blast movement, they recovered approximately 35 to 50% of the sandbags. So still quite poor recovery of the sandbags. And another disadvantage was, whilst they were able to measure subsurface movement, this subsurface movement was not able to be defined until the sandbags were actually uncovered during excavation. And by this point, it's often too late. The advantage, however, was they were able to measure subsurface movement with the sandbags that were recovered. Electronic methods have also been trialled, so by Gilbride in 1995 and this work was continued on by Harris in 1999-2001. This method used metal targets placed in specially designed holes for measuring blast movement, and then obviously detected using a metal detector. The advantage of this method was, again, they could measure subsurface movement, and they could also measure the subsurface movement and the position of this prior to actually excavating and digging the blast. So that was a huge advantage. The limitations they found of using the magnetic targets were quite a limited range below the surface, and only one magnetic target could be used per hole. The signals, they couldn't have the magnetic targets too close to each other, or the signals would interact with each other. Another disadvantage they found was the operations themselves could not be susceptible to damage from these magnetic targets. So you can imagine if one of these targets would have hit the crusher, it could have caused a little bit of damage. More recently, blast movement monitors have been introduced into this field. Blast movement monitor, or the BMM for short, is a system developed and patented by the JKMRC at the University of Queensland, and is now commercialised under license by Blast Movement Technologies, which is now moved under the umbrella of Hexagon Mining. This system consists of electronic transmitters placed within the blast prior to blasting, and then located after the blast using a special detector. The advantages of this system is measurement of subsurface movement. Multiple BMMs can be used per hole. They are more accurate and reliable with increased detection rates, usually documented to be around 70, 80 upwards %. And they can measure blast movement up to depths quite easily to 20 meters. Disadvantage of this system, there aren't many, but they can be time consuming to implement in the blast prior to blasting, and there's obviously a cost involved in using this system. Okay, so all these measurements of blast movement, what have we learned? What do we know about blast movement? What we've found by a number of authors and by studies conducted by myself as well, we've found that direction of horizontal movement is typically perpendicular to the timing contours. We've found that movement is greatest in the mid-bench region of the blast. We've found that inconsistent free face conditions, so by this I refer to choked blasting conditions versus free face, result in variable movement, particularly in the front few rows of the blast. There is higher variability in the direction of surface movement, and this is simply due to the way that the surface of the blast acts as a free face, and hence less confinement. And we've also found that movement in the body of the blast is typically consistent in terms of direction and magnitude. So modelling blast movement. So what are the techniques, what are the methods used to measure, to model blast movement? We'll talk about each of these in turn, but number one is you can use direct measurements. So you can measure every single blast using BMMs, you can use stakes, you can use a combination of these. Number two, which I'll talk about, is movement template. And this is a simple method where it applies the average movement vector, the direction and the magnitude to predict post-blast movement using previous measurements. The stochastic model is a model I've developed myself, which builds on the movement template method. It's a lot smarter and takes into account a lot of the inherent variability in blast movement. And then finally, the Holy Grail 3D blast movement model. We'll talk about that one last. Okay, so a few more case studies. Direct measurement of BMMs. These are all taken from the Blast Movement Technology website. There are multiple up there to demonstrate the impact, the significant impact and the effectiveness of measuring every single blast with blast movement monitors. So a few examples. The Golden Queen Solidarity Mountain Mine was found to save $55,000 US per blast in 2018. The Damang mine in Ghana found $260,000 US savings in 1 month alone in 2019. The Centerra Gold Mount Milligan mine was able to recover over $600,000 US of ore in one blast in 2018. And these examples, there's many, many more, and they're all on the website there that I've included as a source if you want to have a look for yourself. So the effectiveness of the BMM system is well documented and well known. Okay, so number 2, movement templates, which I want to talk about. As a consultant myself, I've travelled to a lot of mine sites, in particular looking at ore loss and dilution and reducing ore loss and dilution. And what I've found is on most sites, when we're looking at just ore blast alone, typically there are 4 to 6 standard blast designs. And these blast designs will depend on rock type, they'll depend on the hardness of the rock, they'll depend on the type of the blast, so trim blast versus production blast. And what I've also found is if these conditions do not change, for instance, if you have a blast at 0.5 kilogram per tonne powder factor in a certain rock type, always fired to a free face, always fired along the echelon, what you'll find is that blast movement generally is the same each time. It doesn't change, not significantly. So the movement template method works on this understanding by applying the average movement vector, so the distance and direction for that particular blast type measured from previous blasts. I'll go into this a bit further with a couple of case studies. So in 2011, LaRosa and Thornton measured 8 blasts at the Placerone mine, and if you look at the top bimodal distribution there, it's quite self-evident that the top flitch of the blast was more or less a horizontal movement of 4 meters, and they measured on average in the bottom flitch a movement of 9 to 10 meters movement. Fitzgerald took it one step further in 2011 at the Super Pit in Australia, and he developed a template method for each type of blast in terms of initiation, whether it was free face, whether it was an echelon or center lift, for each rock type and for each blast type, so production versus trim. I myself conducted a study in 2012 at the Ahafo Gold Mine in Ghana, whereby we found after introducing this template method, we were able to show a better reconciliation between the mine to mill grade and a significant reduction in diluted tonnes for a good part of a year after this method was introduced. So the template method is quite a simple and effective method, and it can use previous measurements to predict what's going to happen next with the assumption that things aren't going to change. So your rock type hasn't changed significantly, your blast design parameters aren't going to change, your powder factor, the way you initiate the blast is more or less the same as the previous. Okay, so advancing on this method, I want to talk about the stochastic method, or the stochastic model. So the stochastic model takes the template model and just makes it a little bit smarter. It accounts for the inherent variability of blast movement. So a little bit of background in terms of stochastic model. The term stochastic is applied when there is a random component to a model. For example, when values of the input variables are uncertain or they are sampled from a statistical distribution. So I'm talking about powder factor, I'm talking about stemming heights, I'm talking about the blast design itself, the direction and magnitude of the blast movement. They're all inputs and they're all variable. The most common sampling technique is the Monte Carlo method, which is what's used in this model. This method relies on random sampling from the probability distribution that is established by the blast movement database. And the Monte Carlo sampling method can model hundreds, thousands of combinations of input parameters to quantify a statistical distribution of outcomes, and in this case, predicting blast movement. So let's expand on that a little bit. So the stochastic model, it assumes that, say, most mine sites had been measuring blast movement. They'll have somewhat of a database of blast movement measurements in terms of horizontal movement and in terms of direction. And these will be applied to each type of blast. So the 4 to 6 blasts that we were talking about previously, there'll be somewhat of a database that we can fit a distribution, a statistical distribution to. So the inputs are the magnitude and the direction of the blast movement. And these statistical functions are then applied to these inputs. We then run simulations. So Monte Carlo simulations are run to generate a range of possible outcomes in terms of the magnitude of the blast movement and in terms of the possible direction of the blast movement. And the output from the simulation is predicted blast displacement with confidence intervals specified by the user. So you can specify you want 80% confidence interval, and it will give you the predicted blast movement within that 80% confidence interval. Bit confusing now, I know, but the next slide I'm going to run the actual example of the stochastic model to break it down step by step. Okay, so here we start with the pre-blast floor boundary. So these have not been adjusted for movement in any way. We have a database of pre-existing blast movement in terms of horizontal movement and direction. We fit distributions to these. And then we run the simulations. So this is currently used at risk, which is just a plug into Excel. Monte Carlo simulation. I'm running 100 just for speed here, but you can run up to hundreds to tens of thousands to predict the movement. This is just to show you how quickly it generates the post-blast boundaries. And there we go. So we have the pre-blast and we have the post-blast 80% or 70%, sorry, in this case, predicted post-blast movement. Okay, so what are the advantages of this model? Well, I hope I showed that it's pretty simple and effective to use in a way similar to the template method, but a whole lot smarter. It incorporates some measured variability in the blast design and the blast movement vectors. And what it does is it alleviates the need to measure blast movement for every blast. In saying this, you still definitely need to measure blast movement if one of those input parameters change. Say if you move into a new pit, or if you move into a new rock type, or you want to increase powder factor significantly, then definitely you need to measure blast movement to calibrate the model. But apart from that, the model can essentially run without having to measure movement every single time. Okay, and finally, modeling blast movement, the holy grail, the 3D blast movement model. So everything discussed so far in this talk has been measuring movement in 2 dimensions. Typically the mid-bench elevation of a blast, or in some cases you can measure in flitches. The 3D model enables not just horizontal movement, but vertical movement and a better understanding of the movement mechanisms. The model will be able to easily simulate different blast designs and timing configurations before the blast is actually implemented and fired, so to optimize the operation and minimize all loss and dilution. The model will also be able to account for interparticle collisions. And of course, the model can be calibrated to actual measurements, so whether measured by BMMs or stakes or whatever method used. So what I'm going to show here is just a couple of quick videos. This is the early model of muck-pile movement system developed by the BRC. It's now called the JKV BOC, or it's been developed into the JKV BOC. More information on this can be gained from the JK Tech website. There's also another similar model being developed out of France called the TBT simulator. So this is the same blast. Before I run it, we can imagine, say, this is an area of low grade. We have a section of high grade through the middle and a section of waste in the back corner. This blast assumes a complete free face conditions and a V initiation. We'll show it from the front and we'll show it from the back. Okay, and from the back. Okay, so to conclude today's talk, I've demonstrated that the magnitude and the direction of blast movement are site-specific and they depend on a number of parameters, including blast design, including the geometry, including confinement conditions and geology. There is one no-fix solution to every single mine. The inherent variability in these inputs causes uncertainty in blast movement predictions. It's these uncertainty in input parameters that make a stochastic model or a stochastic approach well suited or better suited to modelling and predicting post-blast grade boundary displacement. And the stochastic model alleviates the need to continuously measure blast movement for every single blast. Now, I've got a whole bunch of references here which I'll keep up. That concludes my talk, so we'll move on to any questions.